So, welcome to the 5th lecture of the course Basics of Fluorescence Spectroscopy. Until lecture 4, we discussed about the several topics on this absorption, and we ended with the double beam spectrophotometer, right. And here, as you see, I was discussing about this double beam spectrophotometer, and in this case we discussed about the role of this transparent part. This is my transparent part over here, the role of this mirror part over here, but I have not discussed yet this role of this opaque part. So, we can discuss this role of this opaque part. Let us say, and because these two rotating mirror system are synchronized in such a way that when it is mirror part of the first one, this is transparent part for the second one, and you can readily determine this I0 value. So, here I am going to measure this I0, and in the otherwise when it is transparent part for the first one and mirror part of the second one, I can measure this I. This detector is being used for such a spectrophotometer is generally PMT, right. So, the detector is generally PMT. The full form of this is photo multiplier tube. So, in the principle of this photomultiplier tube is nothing but the photoelectric effect. So, photon falls right on the photocathode, we generate the photoelectron. These photoelectrons are being multiplied with by the diodes under negative potential, and these generated electrons is converted to either current or voltage against some resistor, and which is used to measure the intensity of the incoming light. So, if the light intensity is more, that photon is more, so number of photogenerated electron will be more, so the current will be more, and the potential and the voltage, output voltage will be more from the PMT. But these type of devices actually generate electrons even in absence of light. These are called the thermal electrons, right. These are called the thermal electrons. That means there is always some current coming out or voltage, right, against some resistance. So, there is always some current coming out from the PMT, right. So, this current is always present, right, is always present whether you have light or not. This signal from the PMT is always present, and these are called the thermal noise of the PMT. So, PMT always has thermal electron giving you the thermal noise. Now, if you can cool it down, let us say you put the whole system in the liquid nitrogen 77 Kelvin. So, the number of thermal electrons will be much smaller, and there will be not much count from the PMT, right, but that is expensive, right. So, what we can do, we can instead measuring that actual value of I, right. When you are measuring this I, remember when you are measuring this I, let me choose another interesting color over here, maybe this one. When you are measuring this I0 or I at this PMT, right. So, here is your I0, you are measuring it, right, at this PMT. When you are measuring, the intensity coming out from the thermal electron is also added on it. Let me assume that thermal electron intensity is IT, right, IT or ITH. So, here I0 is because of this incoming light plus ITH is because of this thermal electron. So, that is the total intensity, right. So, in the reference channel, this is my reference channel. So, in this channel, right, this is my reference channel, here is my reference. So, this is my reference channel. In the sample channel, the intensity is I plus that thermal electron will all be there. So, this is my sample channel. If ITH is much smaller than I0 or I, then I0 plus ITH divided by I plus ITH will be almost equal to I0 by I, provided ITH when ITH is much smaller than I0 or I. But if it is not, then this ratio will change. If this ratio will change, if this ratio means this ratio will change, then log of this ratio will change, the absorbance will change. So, there will be a lot of problem in the measurement of absorbance. So, somehow I have to subtract this ITH. So, I have to get rid of this. I have to get rid of this term. How to eliminate from my measurement? That is my question, and that is why I have this opaque term. So, as I was telling, this is synchronized in such a way that mirror for the first one means transparent for the second one, transparent for the first one means mirror for the second one, opaque for the first one means opaque for the second one, right. That means I am going to measure some intensity, right. I am going to measure some intensity here. Let me write opaque for first is opaque for second, right. So, in this case what we are going to measure? ITH. So, we are going to measure ITH. Now, you know what is the value of this ITH. So, you can do Y0 minus ITH divided by I minus ITH, and you will get the exact value of the ratio. That means, the exact value of I0 by I you will get. So, the absorbance you will going to calculate in this way will be very accurate, right. Okay. So, these are all about this absorption spectrophotometer, about the instrumentation what I wanted to discuss with you. Now, obviously, we have to move on, and before moving to the fluorescence spectroscopic part in more detail, let me show you one interesting application of this absorption spectroscopy, which will be required in while we will discuss the sulfatochromism in fluorescence too. So, this is important for us also to understand this. So, we have several molecule, right, in our world, but some of them actually show interesting property in terms of sulfatochromism, right. So, here sulfatochromism means so this chromosome means color, right, and this solvato means solvent. So, this shows solvent dependent coloration. So, if you put this molecule in water, it will give you one color. When you will put it in alcohol, it will give you another color. When you will put it in ether, it will give another color, and so on and so forth. So, this some molecule shows such kind of solvent dependent color change, right, and those molecule are known as sulfatochromic molecule, right, solvent dependent color change, and we call these molecules are sulfatochromic molecule. Now, what is the origin of this color of the molecule, right? I said that I dissolve this molecule in water or whatever solvent, methanol or ethanol, and I say the color of the solution is yellow. Why? Right? Suppose you use this molecule, right. So, you use this molecule here, when you dissolve this molecule in methanol, you will going to see a yellow color. So, like yellow coloration. Why? Because this molecule absorb to the blue color, right. So, this molecule absorbed in the blue color, right. So, if I just roughly draw this absorption spectra of this molecule, the absorption spectra is something like this. The absorption maxima is around 350 nanometer, which is down to UV blue color, right, down to UV blue color. So, that is why it is, or maybe it is 380 nanometer, right. Okay. So, this is my absorbance, this is my wavelength nanometer. So, now if you change the solvent from methanol to some other solvent, let us say you change from methanol to water, right, and you see now I am changing this methanol to water, and you see a small change in the coloration, but there is a change in the coloration. So, the color changes from bright yellow to some dark yellow, something like this. Do not go exactly by color, this is just I am trying to tell you the phenomena, all right. So, like this, that means this color was corresponding to this absorption spectra, right, this color corresponding to this absorption spectra, that this color correspond to some other. So, absorption spectra will change little bit, that is why this color will change, right. So, in this case the absorption spectra will be little different, right. It will going to absorb in the longer wavelength, little longer wavelength than what was in the methanol. So, you will see small change in the absorption spectra, right, or like this, small change in the absorption spectra. So, you see the absorption maxima is changed from this position to this position, right. So, there is a small shift in absorption maxima, right. So, there is a shift in the absorption maxima, and this shift in the absorption maxima can be further studied to understand why such kind of change in color takes place for typical sulfatochromic molecules, right. And it has been noticed that there are two different types of shift in the color or change in the color. The first kind is that when we change or we increase the polarity, there is always a red shift in the absorption maxima, right. So, first one is on increasing the polarity of the solvent, the absorption maxima shifted to lower energy, or lower energy means longer wavelength, right, or longer wavelength, right. This is known as positive solphotochromism. This is the case 1, positive solphotochromism, and the other one is just opposite. The second one is just opposite the first one, that is on increasing polarity of the solvent, the absorption maxima shifted to higher energy or the shorter wavelength, right. So, everything is same like this, same to higher energy, or shorter wavelength. This is known as negative solphotochromism. Okay, so let us see what is the origin of this. Before that, let me tell you what is this thing. What is this polarity? Polarity is the property of the molecule by which it is a cumulative property, cumulative result of many different interaction. Ultimately, this more polar means it will be able to stabilize a ion or a dipole more easily compared to a solvent with a less polarity. So, it tells me that how efficiently the solvent can stabilize an ion or a dipole, right. So, the more polar means it will be able to stabilize more efficiently, less polar means it will not be able to stabilize that efficiently compared to the more polar solvent, right. Okay. So, with this definition of this polarity, let us see these cases. Let me take a molecule represented as this ellipsoid, right, and let me draw few positive charge over here and few negative charges over here, signifying that this molecule has a dipole moment in the ground state. So, this is the ground state of the molecule, and obviously the excited state, right. I will have this excited state of the molecule, excited state, right. So, if you remember, we discussed that the nature of the molecular orbital for HOMO, LUMO, they are different, right. So, in some case the electron cloud may be shifted to one end of the molecule, signifying the dipole moment is becoming higher, right. There could be a charge transfer during the excitation. So, it is not necessarily that the dipole moment of the ground state is always exactly same as in the excited state, and more often we see that there is a change in the dipole moment of the molecule upon excitation, right. So, let me take the first case over here, where the dipole moment of this molecule is being reduced upon excitation, right. So, dipole moment is being reduced. So, I just put 2 positive charge over here, 2 negative charges over here. Let me write that this is the ground state having energy for yes, when it is present in a solvent of polarity P1, right. Let us say I put this molecule in a solvent of polarity P1. So, the energy of this ground state after stabilization, right, after stabilization become G1 and this become E1. So, I have this is the solvent. Okay, let me change the color. So, these are the solvent actually right, this is a solvent solvating this dipole, right. So, this solvent of the polarity P1 I have denoted like this way. So, it solvated this species somehow, and when you excite from ground state to the excited state, right, this is your excitation. So, you have excited by, and it takes a very short time, right. So, 1 femtosecond, right, I said the last day. This 1 femtosecond is so short time that the solvent will not be able to reorganize, right. So, the position of this solvent molecule, this will remain as it is, but there will be some electronic rearrangement in the molecule. The dipole moment become smaller than the ground state in the excited state. So, and that corresponds to energy E1, right. Now, let us put that this molecule in solvent with polarity P2. Let us do that over here. So, polarity P2, and I consider that polarity P2, that P2 is greater than P1, right. Condition is P2 is greater than P1, right. So, the same molecule, right, the ground state I will draw like this way, 1, 2, 3, 4 positive charge, 4 negative charge, it signifying that its dipole moment is high in the ground state, and as now the polarity of this solvent P2 is greater than P1, this molecule will be solvated more efficiently in the ground state. So, instead of drawing 2 negative charge over here and 2 positive charge over here, let me draw the 4 of them. So, then this is my solvent. So, I have 1, 2, 3, 4, that means I just want to signify that more stabilization in this case. So, 1, 2, 3, 4. Now, I am going to excite it, right, again is going to excite. The excitation is very fast, the molecule will not going to get time to reorient, the solvent molecule I mean. So, but the dipole moment will change, right, this is electronic rearrangement, plus plus minus minus, and all the solvents will be in the similar fashion, right. Okay. Now, let me designate this energy as, G, G2 and E2. Okay. So, one thing I can do, I can simply plot the relative energy G1, E1, G2, E2, right. So, if I plot G1 over here, so if I plot, this is my G1, E1 will be the higher energy obviously, because in the excited state electronic energy I am putting that much of energy. So, here will be my E1. So, the absorption spectra will be similar to this transition, is not it, this transition. So, the H nu will be equal to E1 minus G1, right. So, this is equal to H C by lambda. So, you will get this as a absorption maxima for this polarity P1, is not it. So, let us name this lambda as lambda 1. So, this is your absorption maxima for in this polarity P1 solvent. Now, once you use a high polarity P2 which is more than P1, then the ground state energy is G2, right. So, because the dipole moment is more and it has been stabilized much more efficiently because of this P2. So, now if I may draw the G2 level over here compared to G1. So, the G2 will be somehow here. So, it is stabilized, right, stabilized. So, this is my stabilization energy, this much is my stabilization energy. Okay. Now, likewise the E2 is also stabilized, but here you see the dipole moment is small. So, the stabilization will not be that much. So, the gap over here and the gap over here will not be same. So, here stabilization will be smaller than in the ground state. So, now whenever there is when you are going to measure the absorption spectra, in this case what you are going to see is this much of transition. So, this transition H nu equal to so, in this case this is the energy of E2, is not it. So, here H nu equal to E2 minus G2, right. So, let us say it is C by lambda 2. Let me write a nu 2, let me write here nu 1. Okay. So, here you see this lambda 2 is less than lambda 1. That means, there is a blue shift in absorption spectra by increasing the polarity of the medium, right, which is referred to as negative sulfatochromism, right. So, this is negative sulfatochromism. Okay. So, what we have seen here that the absorption maxima is shifted to higher energy, shorter wavelength, and that is the negative sulfatochromism. This is because the ground state dipole moment is more than x. So, the key factor here is here you see here ground state dipole moment, let us write it as mu g, and here is my excited state dipole moment mu e. In this case mu g is greater than mu e. So, in this case in the big box let me write mu g is greater than mu e, and that leads to this negative sulfatochromism. What happened when the mu g is less than mu e? That we are going to discuss in the next class. Thank you very much.